Let's start with the next session of the introduction to cellular automata. I'll give you an overview of how our first CA looks and how we create its elements in Grasshopper for Rhino 3D. We will use C# to implement the basic functions of the cellular automata, so the selection of the definition of the neighborhoods and the transition rules. And some other aspects will be also covered by C# components, but we will in this exercise also explore the combination of many other components in Grasshopper, which you should be familiar with already, and how we can link them to our own custom scripts. I've chosen to introduce you to cellular automata since it is a very good basis for you to explore further computational models like segregation models or diffusion fields and related growth models that you can create based on this kind of diffusion models or fields. In addition, it connects very well to the first module of the introduction to programming in terms of the difficulty of the cellular automata model, because in general it's a very basic and simple model, and we can use the programming techniques that we've learned so far. Okay, now let's get our hands on the cellular automata program which I provided for you in Rhino Grasshopper. Please open the file cellular automata _02_2D. In our Grasshopper definition you find the whole program for creating cellular automata, starting on the left side, the green group which initializes the grid that is used for the cellular automata. As mentioned in the introduction, we use a regular grid of rectangular cells. There are two ways to create the grid. I will show you one on a planar surface and one on a curved surface. Then the second part is the core of the cellular automata. Here you find the loop component for which we use the Anemone plugin. So for this definition you need to have installed the additional plugin Anemone. And below this loop you will find the visualization which shows us the development and the current states of our cellular automata. Here this white panel, that's my debug window, which I connect always to the output of my C# components. And on the right hand side you find some additional visualizations that we can use to extrude our 2D cellular automata or the active cells to some kind of building structures. Therefore we use this script, but this is based on predefined Grasshopper components, but I will briefly show you how this works. And on the very right side there are some additional parts to create some more fancy geometries if you want to play around with the generated configuration. This is just to show you that you can continue working with the generated configurations and transform them by Grasshopper to some different styles. By the way, as you can see, I've grouped the main parts of my program into three groups or three parts. So the initialization, the main loop, and some kind of additional visualizations. This is a recommended best practice style to structure your Grasshopper definition. As you can see here on the left hand side, usually I use some components that are just there to receive the inputs that are then processed in this group. So this is very useful to give you a good or a better understanding of the information flow in your script from left to right. and that you can understand from where your information comes from. You can do this even better and having here some components like these that also represents the output of a group of components, sending it to an input. But that's up to you, but as mentioned, I highly recommend you to structure your script in a readable way. But now let's look into our definition. I will start explaining briefly how you create the grid. So we use here this grid tiles component, which is based on geometry on a rectangle that you can draw in Rhino. And this is the boundary for your grid. And then you define the number of columns and number of rows, so how many cells I want to have in the X and Y direction. So if we change this, you see the cells or the sizes of my cells increase, respectively decrease, if I change the numbers that I want to use for my cellular automata. The exterior padding, that's just visualization. If you want to have some gaps between your cells for better readability or visualization, you can add these here. After I created my tiles or my grid, I sent this to this component, which basically generates the polygon center, because in the following I will use the center points as information how many cells I have in my definition, respectively how many cells my cellular automata has. The second part that you see below here, that's a different initialization of a cellular automata. I will come back to this in a minute. I just show you this component. That's the usually I name the components that we work with in terms of adding our scripts, starting with C#, underline, and then the title. You can change the name by right-click on the component, and at the top you can give it a different name. So this initialization, this is what we will look into in this session, how the script works to start with the initial states of the cells. We can visualize what we will do just by sending the states directly to the end of our looping component and preview it. So basically we will generate a random configuration of initially alive or active cells, and this is controlled by the ratio. You can change this to a different number, so if you want to have less initial active cells, you can use the slider, or even have a more dense configuration. And the seed controls the initial random seed for generating random numbers. Okay, now coming back to the different way how you can set up your initial grid. So you are not restricted to a planar surface. You can also use free surfaces. For example, in case of you want to add this cellular automata to a curved freeform facade of a building to generate windows, for example, you can use this quad grid. I've drawn here a freeform surface. Let's look into the 3D view on this side. If I activate the preview for the surface and move here. So here you see this is a double curved surface that I created where I want to run my cellular automata on. So I want to have this grid on this surface. Therefore, just deactivate it again. You see here it's my output. I can send it to the visualization, And what I can do is I can directly link this geometry to my to the mapping of the outcome of my cellular automata, and you can see the grids that are created on the surface, on this freeform surface. They are mapped now on this on the other surface. So this gives you a lot of possibilities to explore applying your cellular automata to facades, to other elements, to other topographies, and so on and so on. But for the sake of simplicity, I want to continue with our simplified 2D planar cellular automata, just to concentrate on the main mechanisms of our cellular automata. And on the right hand side, as mentioned, we have a part of the definition that allows us to extrude our generated active cells to 3D. So if we enable this, you can see I can generate immediately a 3D model, having here these gaps between the buildings coming from this basic setup. So if I remove my gaps in the beginning, I've set it, just give it 0, then it looks more like a continuous build structure. Right. What you see here, these small spaces between these elements, I've added them just to visualize or give you a feeling of a scale. If you imagine these are building structures, then these could be the stories or the number of floors of the buildings. And that's done by this definition. Important is primarily to this cull pattern, which removes the cells that are not active, so having the state 0 or which are dead. These are the white cells, and just selecting these colored cells, the violet cells, and the list that so here I send all my cells. These are 361 based on the grid that I've created, and I return here only a subset, 161. These are the colored cells, and they are extruded, and put a cap on top of it. And with this move, I copy the cells that I created here, because if I only show you these ones, this is the ground floor, these cells are generated by extruding the basic elements. And if I move them and apply here a data tree to this move component, I copy the elements, and this generates this kind of structure. Okay, you can also visualize it, for example, in the render mode. Then you get this more beautiful image, or also a nice preview is this Arctic renderer, which gives you this preview with some kind of shadow, generating nice visualizations. Okay, but we are not so interested in the visualization and playing around with 3D structures. We want to look into the script that generates the cellular automata, which initializes the basic setup. By the way, having these input components allows you also to easily deactivate a group which represents a part of a logical function of your Grasshopper definition, just by right-clicking on the component and disable respectively to activate it, enable it again. Good. So now I can connect my debug window to this out and move it close to my C# component. Here I see all the messages if something goes wrong in my code. Then on this panel I will see the information what was the source of the problem. Okay, so you see here the input parameters. I have the cells. I called them cells, but basically I read the center points, which represents the cells. This is only needed for having the number of cells that are in my grid. If you right-click on the input parameter, you see I have defined it as a list access, and the type hint is point3D because I read the center points of these grid cells. Here I've shown you already, this is the ratio, how many cells are randomly set to state 1. And what we will look at later is if we don't want to start with a random seed or a random distribution of active cells, I can also define the cells that I want to start with as a state 1 manually. But first of all, open the script window. So our famous favorite C# scripting window. We start with a list. You remember lists are defined like this. So you say I want to have a variable or a list that I call ini values. These are my initial values. Could also say initial states. And this is a list of integer values. I could also use a list of Boolean values, true or false, dead, alive, 1 or 0. But for simplifying the processing of the numbers and counting numbers and so on, I use integers, but in the end I use only 1 and 0 as states that I store in this list. Okay, that's the list that we need for now. Let's go to the else part of our script, because here we start if we have no seed points, what we do at the moment, we create a random initialization of our starting grid. You remember there is the random number generator, so I create a new instance of the class random. Here you see I use my seed input value. This is the number that I receive here from my input parameters, and create a new random number generator which is called RND. And I have a local variable cur state which I use for current state of a cell. What we do now is we go through all the cells. So here you see cells. These are the points, but I don't use the coordinates, I only use the number of points. So I know these are, how many do I have? Here 361 cells. That's the number that I call here from this count property of my list of cells or points. In the test value, this is a random number that I generate here, and in the next line of code I ask if this test value, which generates random floating point numbers between 0 and 1, if this is smaller than my ratio, then I set the state to 1. So the ratio is this, the other input parameter of my component. How is it? Here, the ratio. You remember, if I decrease it, I get less initially active cells from my script. This is because then so the probability to have a random number that's below my ratio is higher or smaller. And in any case, I create less state 1 elements. And finally, I add the current status, which is either 1 or 0 if I'm not below my random number, and add it to my initial value list, which then is a list that is as long as I have sent cells or points to my initialization component. And finally, I return this list to my states. This is my output variable. So states this is the list of states of my cells that I return. This is the starting setup for my cellular automata. With these dead and alive cells, I will start the automata. But before we look into the mechanism or how this the cellular automata is implemented, I want to show you, as promised, that I can also start with manually initialized cells. So here I use 2 points. I have internalized these points. So I've shown you can draw points in Grasshopper just by drawing points here from single point. You click the points here, and then you can set multiple points. Then you select the points, and then you've referenced the Rhino points to your Grasshopper script. And if you want to store these points in your Grasshopper definition after you close the Rhino window, you can internalize the data. Means the 2 points are stored in the component. And this is a component which is called point. Here you see the point component that I've used. So you can reference the points, and by right-click on it, you can change its name. So for a better readability of your code, you can rename the components, but it makes it more difficult to identify what this component is doing. But in terms of just storing data, that's not a problem. If you activate the component, you see these 2 icons that are automatically shown. This allows you to move around the points. And what you see when I move around the point over my grid, a different starting cell is shown, respectively a different cell of my grid is defined as an active cell, here the same. And how this works, I want to show you in our C# script now. Let's start at the top. So we again use the initial values, ini values list, in which I store the 0 and 1 values. And I have here this ini index. So this is the list in which I store the index of the cells that are below my point that I can move around here. So how to find the grid cell that is below my point? This is what we do here. So that the first if condition, this says if my seed points, if the number of seed points are bigger than 0, then please initialize my cellular automata, respectively execute this part of the code. We've looked in before to the else part. In the initialization, we create a whole list of initial values that have the state 0. So all cells are set to dead, off, deactivated. And now I want to find these 2 cells and change their state to active, so to 1. Therefore, I use the point cloud class, which you can find once again in the Rhino namespace. Here I provided you the link where you can look into the details. Here I create an instance of my class point cloud, and you put in all the points, so all the center points of the grid cell, of the grid that I've used, the center point of the cells, and this creates a point cloud, which I call grid points. And then I iterate through all my seed points. In my case, I have 2, so that's seed points count is 2. And I define here a local variable grid index, which uses my point cloud object and calls the method of the point cloud object closest point. And here I can say I want to find the closest point in my point cloud to my seed point number 1. So to call an element from a list, that's the syntax for it, this bracket, and inside I have the iterator value I for my for loop, and the index of my closest grid cell, the center point of the cell, I store this index in this list, in the ini index list, which is declared here at the top. So finally I will have two index values in my ini index list. And now I go through this list. So I have another for loop which iterates through all the ini index values. And since the point cloud has the same order than my than the center points of my cells that I've used here, I can call the index from the initial values which I have created here based on the order of the points of the cells that I've read in my C# script. So they have the same order. Therefore I can use these indices. So now I call from this ini value list, which this bracket, and now I want to have the correct index, which is the first and the second number that I've stored in this list. So I call an element from a list to use it as an index to call an element from another list. And I set the status to 1. So this transforms the cell from 0 to 1 below my initial points. Okay, so that's the basic script to start or to initialize the cellular automata. We connect the states, as you see here, to the states ini of my for loop, and originally I have had this output here. And if you see, what you see is that also after starting our first loop, which automatically is executed in the anemone loop, which I will explain you in the next session, I return already the first result of my cellular automata, which has used the first set of rules and changed the status of the neighboring cells. How this works, I will show you in the next session.